also about the Huffman code. So this is just one slide as a reminder here. So basically, Huffman code is a variable length code. So basically, each code word is different length, and basically, it allows us to approach as much as possible the theoretical limit given by entropy that we taught in the previous slide. So basically, this is more like a bottom-up approach. So we start with combining together the events with the lowest probability, and then we group them in a binary groups, so that you know how to and then you use that once you have the tree created. So we kind of group the events, and we join together as with a node the two with the lowest probability, and then iteratively we do this at every single step. So just maybe a side notice here, because I noticed in the previous years this was a little bit confusion. So the tree you can see in this slide is actually very regular, but basically, and this regularity comes from the fact that the newly joined node, so as here, is always the one of the two with the lowest probability, right? So basically, it looks like we are just attaching one more event on the side. However, this is not exactly the case. And for those of you who have tried to play a little bit with the Huffman code with the real alphabet, you will probably notice that it can have much more branches, basically, in the sense that it might be that after joining, adding together two possibilities, there will be two different nodes with the lowest probability. So it basically doesn't have to be as regular as on the slides here. So this is just kind of accidental, which comes from the probabilities. And lastly, we also started the topic on the radio signal, which will continue today, and basically on the radio communication and the use of radio signals. What's important here, of course, is you should be aware that the signal there is a useful signal range, and there is also an interfering signal, which with typically the interfering range being larger than the useful signal size, and that in addition to the noise that we are talking, in the case of radio system, we would also have a problem of interference. So basically, of other people transmitting and their signal interfering with ours. So are there any questions relating to the previous content? Okay, I don't hear anything, and I'm not sure if anybody have you tried to do the exercise or play a bit with the Huffman code with an alphabet, or did you have actually any issues or any problem with that? Okay, well, I assume that's the case. That's right. So in any case, if you got any issues or problem, feel free to write me an email, or indeed come for the consultation. Welcome. I mean, log in for the consultation, basically. All right. So moving on from the radio receivers, we are now dealing with the existing density of two cities in US. So basically, one was the case was studied in the American city. So basically, if you look at the Manhattan in the New York and the city of San Francisco, right, and both are kind of quite vibrant, well-populated major cities. However, if you look at the density of the base station for mobile communication, you could actually see that the sorry, that the image here is actually much different. So basically, when we speak about the concept that we had earlier on the slide, we know that actually typically for many, especially for mobile communication, the lower case, so the case when we have multiple transmitter with lower power but covering larger of area. So this is basically a cell-based communication when area supported by served by one transmitter will be considered as a cell, right? And that this is actually the preferred scenario. And on top of that, we have also so-called small cells and macro cells sites. So basically, well, simplifying a little bit, the macro cell and small cells is the concept depends on the covered area. So basically, small cell typically would cover one block or well, I mean one block, one quarter of a city from right, whereas macro cells would have quite a larger area coverage. So anyway, those are like two, operating mobile system solutions. And as you can see here in the Manhattan, there is, quite densely packed of different mobile stations. What's more, whereas here you can see that the mobile sites are much more scarce. And the question is, do you have actually any thoughts or any suggestions why the density of mobile cells in, let's say, in downtown Manhattan differs so much from San Francisco? Even though the both cities would probably experience similar type of customers or similar type of traffic.
One have skyscrapers.
Yes, that's yes, exactly. I mean, the skyscrapers by themselves, they are not as much of a problem because there are few of the skyscrapers as well in San Francisco, right? But it's like in the sense that it's not the problem of few skyscrapers. It's the problem basically of much denser building, right? So like in Wrocław, if you build Sky Tower, one Sky Tower is not going to make a difference, right? Whereas it's actually what is called an urban canyons. And second idea, which is also, well, to some degree related on the previous one. It's more got to do with the human factor, actually, right? So basically the number of users. Okay, so basically, if you think for the last lecture, I think somebody actually said correctly that cells occupying smaller area, they can serve much more more users in general. And the other problem, which comes also with the high building density, so high building density in the sense of the radio propagation, but also in the density of people, right? So basically, you have more devices, more users per same area, right? And this is basically what you can observe here. So this is the what is often referred as urban canyons, right? So typically construction using concrete, metal, well, especially the metals, can imagine they are very good reflectors for the radio signals. So basically the signal would kind of propagate along the main streets. However, there is a lot of reflections, first of all, but also, the signals cannot penetrate, so far away. I mean, it can just along the streets, but not sideways. Hence, the need for greater density, maybe, with some exception of Central Park, which is again a green open area, right? Where is San Francisco? Well, as you can see, there are like 3 or 4 skyscrapers or high-rise buildings. However, overall, the buildings are much more lower, much more less packed, and also the building materials are a bit different, in the sense that there is more wooden buildings, less metal and concrete used for the constructions. So the propagation looks much more different. Also, another fact might be that San Francisco is quite a hilly city, so it also allows for different geometry types to cover. Okay, so yeah, this is again an implementation of the case here. Now, another thing I wanted to tell in the sense of the radio transmitter is the issue of noise, right? So basically, well, as you're familiar with the idea of noise, I guess, so it's all present in all electronic devices. It's generally created by some random particle movement, so it's like a stochastic process. However, what is important, so the noise that is most commonly used for telecommunication system is so-called white Gaussian noise. Okay, so it is basically characterized by uniform frequency and amplitude, probability in frequency domain, and it is Gaussian because it can be described by the Gaussian statistics, right? But this Gaussian statistic is applied typically to the amplitude level in time domain, right? So this is like the probability of occurrence. However, this is this is not a spectrum of the signal itself. So basically, if you look into the frequency spectrum of the noise, of the white Gaussian noise to be precise, it will have same amplitude on average from minus to plus infinity. Of course, the temporal or local amplitude at a given frequency which will change randomly because that's the definition of noise. However, the noise will be present from minus to plus infinity. And this is basically why very often the noise power is referred to 1 hertz, simply because if your signal is, let's say, 20 kilohertz, it can be easily multiplied by that. And the power density is given by the Boltzmann constant, where K is multiplied by the temperature in Kelvin. So again, thermal noise, basically the higher the noise, the higher the temperature, the more noise. This is also why actually you can see in many systems, most notably where some recent developments in quantum computing, right? You could often see that some devices which are, very fragile to noise. They are very often cooled to the, low temperature, right? Even sometimes as few kelvins. So the particles are like barely moving. I mean, like typically, if at 0 Kelvin, the particles are supposed to be motionless, right? So if you reduce the temperature, your particles are less and less mobile, or moving less and less. Meaning, of course, the noise is generated. You can basically reduce noise by cooling down devices, which is not a practical way, to put something in the cryostat, but with some specific applications, especially with it's needed. Okay, and here's the total calculation, how to calculate the noise, or the noise power density of a signal. Well, you take the Boltzmann constant multiplied by the temperature in kelvins, and then, since we mentioned that the white Gaussian noise is from minus to plus infinity, right? So you just need to multiply this kT with the bandwidth of your signal, right? And the reason being that typically if you're accepting, well, this is kind of the portion of the signal that you can filter out, right? So obviously you're not dealing with the noise from minus to plus infinity. You will have some sort of a filter at the input of your signal, and then depending on the bandwidth of the system, that amount of noise would leak into your electronics. Now, basically, on average, like there is much more noises than the white Gaussian noise that come with different sources. Just name a few. You might have heard of 1/f noise, called also the pink noise, which is basically the name comes from the fact that basically the noise decays with frequency. There's the microwave background radiation, which is just basically some radio signal that is still echo from the Big Bang, which from the fuse, just a time very close to the beginning of the universe, and we can actually still see that or hear that, and many more. Some of them are can be difficult to analyze, and most of the noises are additive. So what does it mean? It basically says that in order to model your noise, you simply add it to your signal, and this is simply exactly the case with the white Gaussian noise. So the most typical model, numerical model of the radio channel, would simply add some noise into your signal once it's being transmitted. And somehow interesting exception to that rule is there are some multiplicative noise. So basically, multiplicative noise means that the noise is multiplied with your signal, and this is often seen as so-called spectral noise in the radar system. So if you decide in few semesters to there is a lecture on introduction to radar technology, and this is elective lecture, and of course, if you decide to choose that one, there will be also some talk about radar systems and also about the multiplicative noise, which is considered to be simply due to the roughness of the surfaces. So you are illuminating surface with your radar signal, and basically, because of the roughness, there will be some disturbance in the signal that you received. And with this example, you can actually hopefully imagine that in that case of multiplicative noise, if you increase the power, your noise will, also increase, right? So which is typically a bad news for the system, because whatever you do, there's no way of getting rid of multiplicative noise. Again, for the additive noise, if you increase the power of your signal, noise becomes the same. So actually, you can get a better quality of the signal, and this is very much reflected into the signal to noise ratio, right? So this is what I told earlier when we discussed basically SNR and signal to noise ratio, which is the ratio of the signal power or signal amplitude to the average noise amplitude, right? And this can be used as a good metric to assess the quality of your signal, exactly because the noise you're assuming is additive, right? So basically, if you increase your power, the SNR will also increase. Okay. Interference. Now, interference, this is kept separately from the noise because it is with something which is artificially generated by humans. Okay, so there is a language issue over here, because very often on the physics classes, right, you may hear about constructive and negative interference, which is basically, got to do with the fact how two different waves interact with each other, right? And superposition and all that. And in the next lecture, and when we go to Earth antenna and propagation, we'll also talk about this sort of interference. However, here this is taught in a slightly different context. So we are not talking here about two well-defined coherent signals when you can understand the phases, but in the context of radio planning, interference is considered as a sum of all the human-generated signals that are out of your control, basically. Okay. So for example, by the way, in Polish language, actually, this would be called more zakłócenia as opposed to interferencja. So in Polish language, those two terms are clearly separated. In English, the word interference is unfortunately used for both, which might be confusing. Okay, so you should kind of keep in mind that the interference we are talking here is more somewhat uncontrolled quasi-stochastic process. Quasi-stochastic because it's human generated, but we don't have control over it. Whereas, as opposed to the interference of coherent waveforms, wave signals. All right. So basically, a good example of actually interference would be, you might have, especially in student dormitory, expanded that when, again, not in student dormitories, because there is like probably one big Wi-Fi. But anyway, if your neighbor has a Wi-Fi router and you have a Wi-Fi router, and by any chance you didn't set it up to they both operate on the same channel, this is exactly where there is a case of interference. So basically, and it may cause slowdown of your internet, especially if the routers are physically relatively close to each other. So basically, what may happen is that you are using the Wi-Fi, and then because of your signal, your Wi-Fi router kind of clashes or collides with your neighbor's router. And this goes back to the principle that we said earlier on, that you cannot simply transmit. I mean, you can, but it's not a good idea to transmit the two signals at the same frequency, same space, and same time, because they would collide. And in case of Wi-Fi, there are some protocols of dealing with that, but still you would experience, because of the interference, you might experience slower internet speed or slower throughput. Okay, so typically when we speak about the standardization, of course, you, as I said, this is something you cannot control, but typically when you are doing or building like any radiating electronic device, there is a telecom permissible interference. Okay, so basically this means that any device, and any radio device that you're building, firstly, it cannot create significant disturbance to other devices. So basically, you should be nice to your neighbors, right? That's like a technical requirement. But also, you should build your device in a way that it can accept some level of interference without deteriorating performance. Okay, so those are like the two conditions. So in a way, the first sentence says here that you should be nice to your neighbor and not generate something that signals that could create the interference to them, but you should expect that they are not nice to you, right? So basically, if they create interference, your device should be more or less able to deal with that. Now, this is, of course, the formal definitions, and as you can see, it is stated quite vaguely. This is, of course, because this is a high-level definition, and the exact amount of interference that you should expect or you should transmit, that depends on different systems. Okay. Right. So basically, when we say in using interference, there is again quite a few types. There is the electromagnetic interference, which is basically some electromagnetic signals induced into your electronic device. There's the crosstalk, intersymbol interference, and so on and so forth. So it basically can take multiple forms. In this lecture, I don't think we'll be talking about all of them in details, but just basically, I wanted to point out to some problem here. This is again given in the example of the UK, and you can see here that's the map. I believe it's of the UK. And basically, general rule is that every radio systems, apart from usable signal, generates some sort of interference, right? And this is because of the very first the slides that we talked in the review today, that there's always some area where your signal is not useful anymore, but again, it's a weak signal that still propagates. Okay. So another thing is that there is an issue of out-of-band emissions. So, for example, from what's called intermodulation of products and nonlinearities of radio devices, I believe this year we will have I would like to dedicate special lecture on the electronic and on the intermodulations and nonlinearities and how it works in real electronics. But basically, in this context, it means that if a radio device is not designed properly, it can generate certain signals that are out of the allocated band for that device, right? So, for example, if you have bad Wi-Fi router that was not properly certified, in addition of operating at 2.4 gigahertz, it may generate additional signal at So for 2.4, that will be, let's say, 4.8 gigahertz, so double the original frequency at the first harmonic, right? And uh, even though the signal might be, very small, it can still, contribute to increasing this noise, right? So another thing are side lobes of antenna radiation patterns. So basically that, you think you have a good antenna, but either your antenna is not designed properly, or again, it was tilted because of some, environmental conditions, right? So we are radiating some energy into area which you are not supposed to. Then again, you might have some noise from different transmitter components. And all of that, as I mentioned, there are typically very, very small signals. However, if you add them cumulatively on top of each other, that can have like a significant impact on your radio signal, and this is called radio spectrum pollution, right? So, well, this is something actually for those of you can, it's pretty much similar effect if you want some analogy, if you have ever, watching stars at night, and it's quite analogous to the idea of the light pollution, right? So if you're in the countryside or somewhere remote places, you will notice you see much more stars than you do in the big cities, right? And of course, this is because of the street lamps. But if you have a single street light, that's not something which would typically bother you that much, right? I mean, the single street lamp is something you can, cover with your hand or whatever. So just one wouldn't really spoil your view of the night sky. But if you add a number, like thousands of them, at different locations within the cities, overall, the created signal can really change the night sky view, right? And what you see here, this is more or less similar, right? So that typically increases the noise level. Now, the question is, right, and this is what we are calling here. So C, this is our carrier frequency or our useful signal. And here in the denominator, we can see N, which is noise, plus I, so interference. Okay, so basically, we can see here that this is called signal to noise and interference ratio. And simply we're treating here interference as some sort of pretty much same as noise. But that's the explanation. So, well, what can we do here? And this is, of course, something that we can do. Our intuitive approach is that we can, of course, again, we know this all is supposed to be additive, at least the noise. So what we can do? Well, we can increase our carrier power, our C, right? But can anybody predict why this is not necessarily a good idea? Okay. So basically, if you think about your radio transmitter, and you realize you have very slow Wi-Fi just because your and from this lecture that your Wi-Fi is weak because your signal to noise ratio is very poor, right? So what you can do, well, it's as I mentioned, ratio of two factors, the signal and the noise. One solution would be if you can live in a cryostat to decrease the temperature of your room. That could definitely help reduce the noise and improve your quality signal. But I suppose not many of you would like to live comfortably in sub-zeros or lower temperatures. So I'm guessing that's not an option. So the other option, of course, is what we said here. You can increase the power of your Wi-Fi router and the power of your signal. Okay. And again, why do you think it's a good idea or do you think it's a bad idea? So maybe let's do the visual thing. I would write in the chat, sorry, two options. So who thinks, just increasing the power of your Wi-Fi router to get higher internet is good idea? And who think it is not? Oh, yeah. I see some replies. Okay. So obviously, okay, that's interesting. So it depends on what, or can you elaborate a little bit? What's
I think I heard that increasing the power is good to some point. After that, you need to work on your antenna.
mm, okay? So yeah, this is. I mean, yeah, well, okay. Working on your own, yes, that's working antenna. It's a different story, and we hopefully will talk about that later today, and how this can be done. So, okay. So generally, actually, the answer is it is not a good idea. Okay, or at least not for a radio system. Uh, Although, well, the answer it depends. It would typically work well, actually. So indeed, there are some conditions where you might use that. For example, when you are when you have an isolated system, right? So if you think about the transmission in a cable, then you just increase your power, and well, unless you burn the power, this should be generally fine. Or okay, well, there are nonlinearities of your amplifiers that okay, let's not go there. Maybe it's not that obvious either. Um, yes, there's okay, Milos. That's actually a good comment. It could be fine to increase the power. Yes, this could. You have to be a bit careful here, right? Because then you need to be able um, to point out, exactly the areas that you want to cover with your antenna. And as we'll show later on, you need to be careful about what's called side lobes. So it's not always that easy to be selective with your antenna. But I mean, in general, yes, if you can kind of isolate and limit your area, that could work without interfering. And of course, the reasons why it's you get it correctly, that why it is supposed not to be a good idea is that after you increase your signal, your neighbor will do the same, right? So this is something like race to the bottom, in the sense that at the end of the day, if everybody just keep increasing their signal, you would create, as a matter of fact, more interference, because what's useful signal to you is interference to your neighbors. So on a systematic levels, in general, it's a not good idea. However, as it was, correctly pointed out, especially by Milos, if you can narrow down and be more selective, to direct your beam, this actually might work, right? Okay, so that's okay. Now two terms which were kind of earlier on, and this is what happens when you transmit out of your bandwidth, right? So typically, of course, we well, in any electronics, but especially in the radio systems, we use quite a lot of filters, right? But as you should be aware by now, realization of perfect filter. So by perfect, I mean, the one which cuts you off at certain frequency is not possible. And if somebody can tell me why is that? So why you cannot realize a perfect filtering with rectangular filtering function? So we think about like 90-degree slope of filtering. It was, I believe, mentioned 2 lectures ago, although
is it the same reason why you can't have perfect square wave? You need infinite components.
Exactly, right? Because there is what I mentioned earlier, the symmetry between the Fourier and inverse Fourier transform, right? So basically, in order to have like a perfect rectangular filter, in time domain, you would need to know your signal, well, from minus to plus infinity, right? So basically, well, unless some of you can build like a time machine, it's called non-causality, right? So you cannot really know analyze the signal before it occurs in your device, right? So that's indeed the problem. And yeah, and that was a very good answer. So as you pointed out, this is exactly the symmetry between the time and frequency domains. Okay, so as we know, we need to deal with imperfect filters. Also, even assuming your filters are well designed, there are some other factors to consider, such as, for example, Doppler frequency shifts, right? So you think you're transmitting, imperfect signal at exactly the frequencies that you're allocated, right? But once you get into a car and start driving reasonably fast, just because of the Doppler shift, your frequency will be shifted out of this perfect band. So, and this is basically 2 types of what's called out of band emissions and spurious emission. So typically, out of band emission we talk when, due to some factors such as imperfect filtering, filter slopes or some Doppler shift, your signal exceeds a little bit the bandwidth, right? And again, this is something which typically frequencies that are in direct proximity of the bandwidth. And then, so that's the definition. And then we have what's called spurious emissions. And spurious emissions, they are generally consequence of the nonlinearity. So both would occur out of the bandwidth that you're allocated for the signals. However, spurious emissions will be much farther away. So for example, if you think about higher order harmonics or intermodulations, so this is basically some additional components, side effects of your signals. And again, we'll talk about that later on. So I can move on, I guess. So this is just an illustration of, I was telling. So this is a perfect case, already taking into account some filtering slope. And typically we will have, of course, this delta F. This is what's called a guard band, right? So typically, especially for frequency division classical FDM systems, you would allocate very narrow frequency bandwidth on both sides of your spectrum, exactly to accommodate, the certain inaccuracies or movement when your frequency shifts. And what's of course important that this this will again depend on the system. So for example, if your system is supposed to work with objects that move at high speeds, so let's think about planes, let's think about high-speed trains, even cars in certain conditions, you would probably need a little bit wider margins, wider guard bands for classical frequency division multiple access systems, okay? Because again, the Doppler shift is quite a typical reasons why your bandwidth will change. And then in reality, this is more what we expect. So over here, we see that the center frequency is shifted towards the right, towards the higher frequencies. That's again the Doppler thing. But also we have some emissions here, and portion of that goes out of the bandwidth, and that's exactly the problem of the interference that we are generating. So in that case, this interference is maybe generated to a different system or different channel, right? So it's not anymore this case of you and your neighbor using the same Wi-Fi channel. In that case, you have, you both were smart, have degree in engineering, and you agree that, okay, you take channel 3, I take channel 5. However, if the quality of your router is bad, you may still generate some signals, even though in theory you're separated by two different frequencies. All right, and with that, I wanted to move on to a thing which is called link budget. Right, so actually, maybe are there any questions towards the intermodulations, out of band emissions, or anything related to the radio signals so far? Okay, wait, I can hear you. So well, I think that's quite understandable. So we want to link budget, and this is something which typically allows us to calculate a power that is still well able to receive, being received by the receiver. So typically, what's happening with a typical radio signal? We got a transmitter with all the blocks that we discussed earlier. So modulator, channel coder, source coder, blah blah blah. Then we have the transmit antenna, which radiates our signal to the unbounded medium. There is a propagation path. We have a receive antenna, and then we have receiver, and here the modulator is kept somehow separately for the reasons you will see soon. So basically, if you think about different phenomena or how you can each of those components, it can either amplify or deteriorate your power level. So how does it work? Well, here on the transmitter side, we have a certain signal that is being generated, and then I should put it this way, and then that signal goes to the antenna, and as some of you pointed out correctly, right, the antenna got certain focusing capability. So actually, you can use that energy, you can focus energy to boost the level of the signal. So actually, you can have locally after antenna at some point more energy than sorry, not really more energy, that's the wrong term, but you can simply boost your signal at certain directions. Let's use this. Then we go through the path loss, and as we know, the signal deteriorates with the power 2 of the distance for the lossless case. Again, that's still lossless case. So that's actually very quick, right? So we'll end up over here. Well, luckily we have the receive antenna, which can perform exactly the same trick as transmit antenna. So it can selectively focus energy. And then it's up to what's called receiver sensitivity. So for the purpose of link budget that we'll be calculating here, we'll be simply assuming that there is a minimum power threshold for the receiver to be able, to perform this communication. Okay. Then, so typically the signal from the receive antenna, it will go through the low noise amplifier. So the idea here is that you actually want to, it's not always possible, but you typically want to extract your signal or boost your signal with amplifier. But as you know, your amplifier typically will also generate some losses because it's a semiconductor device, and there's losses. However, with the low noise amplifier, your aim actually is to boost the signal much more than the noise itself, or basically not to add any other noise. So this, for low noise amplifier, actually it's this red arrow was supposed to symbolize noise. However, this is not accurate because it's, well, you can do some averaging and things like that, but typically it's not that you are reducing the noise with the low noise amplifier, you're just trying not to add much more noise. And at the end, for the demodulator sensitivity, so if we think again here about the IQ plane, it's again the ratio of the minimal signal level for a given modulation. So again, over here, we are looking to increase our SNR, so our signal to noise ratio, right? So again, we try to get strong signal and as little noise as possible. So again, for the calculation of link budget, we'll pretty much stop here without going into modulation. So we'll just assume there is a minimum receiver sensitivity or power level that will, allow desired modulation to be transmitted, to get across, without breaking that down into different types of modulation or different techniques for coding. But this is kind of underneath, so included in this minimum power. And this graph is of course not to scale, so this draws dramatically down. Okay, so this is basically the philosophy of the link budget, and not sure if there are many questions. Well, if there are any questions here. Okay, so this is just to understand the significance of the link budget and understand different components and what it's doing. Okay, so we'll do some link budget calculations, but I think just a quick reminder of the logarithmic or decibel scales. So I'm assuming you kind of had that already. So again, this is just a reminder. Okay, so typically when we have the power ratio, so bell or decibel is the power ratio of a signal to some reference power, right? So typically we would use like either 1 watt or 1 microwatt. And traditionally we are not using, so logarithm base 10 is the ratio of the power that we're investigating to usually 1 watt. So it's basically a relative metric. Commonly used is a decibel, which is 10 times the ratio. That shouldn't be surprising. I mean, that's decibel for 10. Now, here's part that comes sometimes confusing. So when dealing with voltages, this can be often referred to as 20 logarithm base 10 out of voltage 1 compared to voltage of reference. And can somebody tell me actually why is that?
the resistance is the same.
Sorry, can you speak up?
There's square.
Exactly, right? So very good. So if you think about the, the typical equation, well, power is of course voltage multiplied by current, which again can be, well, in general it is proportional to the power 2 of voltage, right? So this is when, since this is a logarithm, you can take the power 2 out of under logarithm outside, which is seen as multiplication by the factor 2. All right, and this is exactly the reason why sometimes in decibels you would see the when dealing with power you will see the 10 logarithms when dealing with power and 20 logarithms when dealing with voltages or currents, right? But this is exactly this power 2 factor, and hopefully this shouldn't be really confusing. So it is still the same metric, right? Just when dealing with voltages, you need to remember that it's typically voltages are proportional to the power 2, hence multiplication by 20, not by 2. All right. Now, yeah, this is basically the explanation we state here. So of course they're proportional or inversely proportional, right? But that doesn't that still the argument holds. And also the same is true for the radio signals, right? So for the radio signals, we typically operate with electric and magnetic fields rather than voltages and currents. But again, same story, right? So the electric field to the power, so the power of the radio signal is typically proportional to the amplitude of the electric field raised to the power 2, and that principle still holds. Okay. So now I mentioned that the logard decibels are a relative scale, and sometimes to avoid confusion, there's like a small letter added at the end after dB, which is basically to denote what is the reference value here. So if we speak about the reference is 1 watt, then dBW, capital W. If it's a milliwatt, then dB small m for milliwatts. That's the convention. Then when we're speaking about antenna gain, which will be in the next few slides, antenna gain is typically by definition dimensionless. However, typically we would use the isotropic antenna as a reference. Hence, dBi for isotropics. So isotropic means simply antenna that radiates the same amount of energy in every single direction. And then if you want to include circular polarization, you'd use dBic. This is a little bit more advanced concept that includes also the polarization of the antenna. And then if we speak about so-called path loss, this is considered as an attenuation. This is dimensionless, so it's simply dB without. So you're basically comparing to one, right? So this is something to keep in mind, right? Especially if you have two values, one expressed in dBWs and the other one dBm. Bear in mind there's like a 30 decibels of difference between the two, right? Now, easy way to calculate, and I think I will not hold it here, but this is, I think, the whole reason why I believe that decibels scale is helpful. I mean, it is a learning curve to learn that at first, but once you do it, you can very quickly perform quite a lot of calculations in your head without using any calculator, which it's actually advantages, especially on meetings with customers when you don't have any advanced simulation tools. So the general rule is the multiplication in logarithm scale corresponds to corresponds to addition, which is which is the main reason why it is useful. Now, typically positive decibels, so above 0 means sort of amplification. Negative dB means attenuation, right? And what is nice that there are basically only few values that you need to remember in order to calculate things in head. So typically, well, 0 decibels, this corresponds to 1 because anything to the power 0 is 1. Then 3 dB corresponds to factor 2. And then -3, of course, it will be half. And then since we're using logarithm base 10, well, it's 10 times. 10 decibels is a factor 10, 20 decibels is factor 100, and so on and so forth. And basically, the reason why it is useful is that if you're operating in decibel scales, you can always break that down into at least approximate sum of factors. So if I ask you quickly to calculate 13 decibels in a linear scale, how you can do that or how much it would be? Okay, so bear in mind, this is really very, very quick. So typically, you can express 13 as a sum of 10 plus 3, right? Basically, 10 is corresponds to factor 10. So 10 plus 3 in the decibels corresponds to the factor 2. So we have a factor 10 and factor 2. And we know addition corresponds to multiplication. So in the case of 13 decibels, it would be actually a factor 20, right? Is that more or less clear for everybody? Okay, so another one, and we have a 70 decibels, and maybe let's move actually to the chat. That would be more convenient. So can anybody type me the correct solution of how much 17 decibels would be in linear scale? Or how we can break that down actually? Or is it totally unclear what I'm talking right now? Okay, why do you think it's 80? Can you, can you break that down or produce an argument to support this? Mr. Bafour? All right, so just as a hint, hopefully this helps. Right, so again, if you have a 17 dB, you can break that down into 20 minus 3. And from the table, you should know what is right. You got it here. So what 20 decibels corresponds to? Yes, very well, Milos. Right, so so basically, just to break that down, what Milos wrote correct answer. So basically, what we can see here is 20 corresponds to the factor 100, whereas -3, because you have to keep the sign, corresponds to corresponds to half, right? So basically 20 means 100, minus 3 is divided by half, so at the end of the day 15. Now let's try, and that's the last one, but I really do encourage you to practice that. If we try with actually minus 1, let's make it as a power in. So we get minus 9 dB watts. Okay, how many watts that would be? Yes, so this time Michał is correct, right? So it's 1/8 simply because it is minus 3, minus 3, minus 3. So basically 3, 3 divisions by 2, right? So 1/8 of a watt is minus 9 dB watts, whereas actually 1 watt would be simply 0 dBW. Right, so 0 decibels always corresponds to 1 in linear scale. Okay, right. So I really encourage you to practice that scale because, well, the reasons why we use decibels is to allow you quick calculations, and typically, usually at the exam there is at least one task which involves some simple calculation of a link budget. All right, so and usually on the exams there is not that much time to do all the tasks quickly, right? So this is, I think, when this calculations comes handy, because you don't need to waste time of thinking. You can just quickly get the answer to the question and move on to the next one. Okay, so time is of a constraint, and this is just something that I put into practice. So by the way, this actually, for those of you who asked in the last lecture, so apparently the legal limit for AIRP is 100 milliwatts, so 20 dBm. All right, and then again, this is a kind of example how this can be calculated. So I'm not going to go through that as we are a bit low on time. But right, I want to move on to the next section. Okay, sorry. Are there actually any questions relating to what we talked so far here? So, I mean, my understanding is that you all are kind of familiar with the decibels and the logarithmic scales and how it operates. It's more a matter of practice and trying to get familiar and trying to do the calculations quick. Because believe me, it's really worth practicing, and it will come in handy in many ways later on. Okay, and now we move to the section of on antenna and link. So before actually we move on the link budget calculation, just a few words, maybe what antenna is. And here you can see like a few examples of different types, sizes, and applications. So from very large, so this is basically antenna used in a radar system for ballistic missile detections. This is antenna, well, it doesn't look like, but it is actually a monopole antenna operating at very low frequencies, highly miniaturized. We know, wearable antennas on top of watches, antennas embedded into a, so this is actually not, well, there is one more antenna here at the beret, but we can have antennas embedded in a form of cloud. So in that case, actually, that's some military application of having GPS antenna integrated into military beret. This is former RCB observatory. So as you might be aware, this site actually does not exist anymore. So last year, I think the site collapsed and this reflectors fade onto the main dish. But it used to be for years the largest radio telescope for observations. And you can see here you have like a dish with, I believe, 200 meters diameter, which is basically like a similar to what you see on a satellite dish, just of course much larger, with the receiver antenna on the top. This is something you might see in airports. So this is like a full body scanner, which operates at 200 gigahertz to scan, and it's basically very advanced form of a high frequency radar system. And here there's some military applications. So anyway, the message here is that the antenna can have multiple ranges and sizes, shapes and sizes. But in general, this is an interface between, interface in the quotation mark, because what antenna does by definition is transferring electromagnetic wave from a bounded medium, like a cable waveguide, into an unbounded one, okay? So it's operating at the boundary between the two worlds, and as such, it has like two types of parameters. So one, if you look from this side, it can be classified by a range of circuits. And so, just a normal circuit or device electronic that you plug into your electronics. And as such, it can be described as pretty much any high frequency or radio circuit that you would use with certain impedance, called here input impedance, reflection coefficients, bandwidth, and so on and so forth. However, on the other side, it has also, my apologies for this, that's the noise temperature, the last one. It can be also classified by the spatial set of parameters. So basically, that would be how it radiates into the space, and we will go just through few of those in this module. But what's important that if you think about the circuit parameters, well, similar to any electronic circuits, those parameters will change with frequency, which is quite expected. Similarly, all spatial parameters, so polarization, gain, the focusing capability, this will also change with frequency. But on top of that, it will change also with direction. And by direction, we mean two-dimensional, so theta and phi, so spherical, two different axes, and polarization, right? So overall, when dealing with spatial parameters in the unbounded medium, it's much more complicated just because the number of variables suddenly increase. It's not only, you don't need to worry about how your antenna behaves versus frequency as a function of frequency, but even here you have at least 4 different parameters. So that's a 4-dimensional space, 4-dimensional equation. Okay, going back to the isotropic antenna. So this is basically antenna that is radiating the same amount of energy in every single direction. But what is significant that this antenna, cannot be realized in practice. Okay, so, and the reason for that is that the electric field is not a scalar, it's a vector, right? So, and if you think about that, well, we have a continuous sphere, which is a very specific type of geometry, of topology, in the sense that, you, contrary to the classical plane, if you move on a sphere in a straight line, you will, end up at the very same space that you started, right? And that puts some mathematical limitations on what is feasible. And if you know, there is a theorem which is called Hedgehog-Combing theorem. That's loose translation. So if you think about vectors which are oriented on the sphere, and if you try to basically comb them in the sense that you try to align them all together on a sphere, you will soon realize that you need at least one place where the vectors would go against each other, right? And that's point of when they're going against each other. This is something like our pole, where you cannot, you're because of negative interference, your amplitude will decrease. Okay, so basically you cannot comb vectors on a sphere in a continuous way such that there's no point when two vectors will have, arrows opposing each other, meaning, negative, destructive interference. And I'm using here the interference in the physical sense, right? So a superposition of two coherent signals. Okay, so it can be realized. However, as said, it's a very good reference antenna. Why? Well, simply because it can be, it can be calculated by a very simple equation, right? So we get the power that gets in to the antenna, we divide it by 4πr square, and that's it. Now, we typically want to characterize our antenna or focusing capabilities of our antenna. And this is something which is typically known as either a radiation pattern, or there's a different parameter called antenna gain. So basically, radiation pattern, this is a two-dimensional function of theta and phi. So it's typically calculated over a full sphere. And it basically shows us the density of signal that is directed into certain areas. So this is exactly this, focusing capability of antenna that we were talking earlier on. Now, what is important here is that this is typically normalized to the maximum of the antenna, right? So typically, because of that normalization, this is done basically for measurements reasons, out of convenience of measurement. So basically, if you just take normalized radiation pattern, it gives you spatial distribution of how your signal will be focused. However, it will not tell you what is the power in that direction. Okay, so and in order to know the power, we need to we'll use here this isotropic antenna, right? So basically, what we are doing, we are checking the power received by your antenna at a certain angle, theta and phi, and at a certain direction, of course, at a certain distance, of course. And we compare that with the energy that you would experience at the same point from isotropic antenna. Okay, and well, why this is convenient? This is very convenient because now we don't need to worry about how far from antenna we are, right? Because from the antenna perspective, the energy will decay the same way from isotropic and from non-isotropic antenna. So basically that removes the distance from our equation, and we can characterize only the antenna by itself, right? So basically here comes the definition of our gain, which is basically the power density radiated into certain direction by our antenna when fed with some power P in, compared to the isotropic antenna radiated in the same direction when fed with the very same power, and of course, over measured over same distance, right? So again, this actually gives us characterization of only the antenna, irrelevant of the power that we fed into that antenna, and irrelevant of the distance over which we have to communicate, and only as a function of two parameters, two angles, spherical angles, theta and phi. Now, the question here, if you know this definition, what is the gain of an isotropic antenna then? And I wait for your answer in the chat. You can type either linear or decibels as long as you specify which one it is. Okay, so bear in mind that as I mentioned earlier, the gain is the amount of power in certain directions compared to the power radiated of the isotropic antenna. So, and of course, Jakub is correct. This is 0 dBi or 1. Okay, right. All right, that wasn't supposed to be difficult. Now, okay, my apologies. This is it's an actually important, significant mistake. Sorry for this. Okay, now usually in that lecture we will actually use antenna gain, but to dig like more specifically into this problem. So right. So basically, when we define the antenna gain, we are using what's called power accepted by the antenna under test. Okay, and why is the term accepted? Because it means we are measuring our the energy that is not reflected from antenna input. So that includes anything that happens to our signal within the antenna, and that might be different losses. On the contrary, there's a term called directivity, which it's just a notion, but we won't be talking much about directivity here. So directivity already deals with the power that is radiated. So somehow artificially, after antenna, which you can imagine in practical purpose, this is not very easy to measure. But the difference between the two is so-called radiation efficiency. And the efficiency is understood in a classical way with electronics. So basically, radiation efficiency accounts for losses that occur in your antenna due to conducting, due to any sort of dissipation energy. So if you have a lossless antenna, your energy is 100%, which means your directivity will be the same as gain. Okay. Another important notion here is that, and again, this is one of the aspects where the English nomenclature is not that good, because I have to underline that when we speak about antenna gain, this is gain in the way of focusing energy, not as you would have amplification in the amplifier, right? And so even though it can boost your signal for a certain direction, it can do that only by focusing. So by taking energy from other direction and putting that into that one, right? So important thing is that antennas, as a general rule, there are a few exceptions, but that's really marginal. From the point of view applications, antennas are passive devices, right? So they can be modeled from the circuit point as usually as RLC circuits. So there is no way of a signal being amplified in the same way as you would have with transistor with classical amplifier, okay? Whatever you get, improve at certain directions, need to be taken out from some other direction, right? And that's quite significant, right? Because that actually means there are some constraints in using your antenna. Okay, so that basically means that, for example, you cannot have antenna with high gain, which has with very high gain that has omnidirectional coverage. You have to decide, either you focus and you boost your gain or energy, or you're fine with lower gain but wider coverage. And again, just as a sort of example, that's probably the most classical antenna type, which is called half wavelength dipole antenna, which is basically two pieces of wire, each quarter wavelength long, forming one half a wavelength, sorry, in total. And what you can see here, this is basically the radiation pattern in theta, two-dimensional, so in theta and phi of such an antenna. So this is really the most simple thing. And typically the gain of such an antenna would be 2.15 dBi compared to the isotropic one. And there are two factors. So as you can see here, the pattern is like a torus shaped, which means you got two directions which are nulls, will radiate practically no energy, and this is the directions towards. So this basically two patterns are aligned. So the direction you're looking at the top and bottom of your antenna, there's no energy radiated. Whereas so that's the implementation of the fact that I mentioned to you earlier, that you cannot comb vectors on a sphere in a continuous way without having some nulls over here. And then because we have the nulls, again, that energy, we remove that energy from the two directions, so it has to go somewhere. So that's why the gain is in that case 2.15 dBis, right? Because the antenna we are assuming here is lossless, so the energy taken from the top and bottom have to go somewhere else. Hence, we are doing better than isotropic antennas. Okay, is this more or less clear? Are there any questions? Okay, I hope I was not rushing too much with the lecture. Okay, so I propose it's 1:45, so I think we will stop maybe here. Just was one kind of example of how antenna radiation pattern can look is more or less like this. This is the shape that you would very often see in your in catalog data for antennas. So what you can see here, well, sorry. So this is of course few of the parameters that are relevant from the spatial point of view. So the most important is called the gain, or actually this is a maximum gain. So assuming here is the power, so okay, first of all, on the vertical axis, we have the amplitude, expressed here again in decibels, that's the common practice. And on the left, we have an angle from minus 180 to plus 180 degrees. So this is basically only one single cut through our sphere, for our radiation pattern. And then the gain is again in dBi defined as how much this maximum gain, how much at the main direction we are doing better than the isotropic antenna. We have here the main lobe, which is typically the main direction in which we want to focus the energy. So the direction of our receiver or receivers that we want to communicate with. And similarly to the terms knowledge used in bandwidth. So we have what's called half power beam width, not bandwidth, but beam width, because we're referring to spatial beam, which is typically referred to the 3 decibels below the maximum level, right? So when we're speaking about the beam width of certain antenna, this is basically the difference between the two angles where the radiation pattern drops 3 decibels below the maximum level. Okay, and I think with that I will let you go, and we continue on. From next week from this. So again, if there are any questions, you can either ask them now or there will be a consultation time starting in 10 minutes. All right. If not, thank you very much for attending and for listening to me. And I wish you, as usual, nice weekend and take care. And thank you very much.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you. Thank you.